greatest pleasure for me to welcome you to the next session, Natural Science. The first presenter will be Marcin Stokowski with presentation the characteristic of the carbonate system in the Odra River estuary. Please welcome.
Thank you. Hello. Thank you. So yes, good afternoon. My name is Marcin Stokowski, and I'm first year student, a PhD student in this institute, the Institute of Oceanology of Polish Academy of Sciences. Today I would like to present the characteristics of the carbonate system in the Odra River estuary. The research was conducted in 2016 and it was founded by the National Science Center. Carbon. Carbon is highly essential and crucial element for life. Carbon builds a structure and provides the energy for living creatures. Carbon is found everywhere on Earth, and we are made of carbon. We eat carbon, we breathe carbon. Our civilizations are built on carbon. We travel with carbon, by carbon, and our economies are built on carbon. One atom of carbon travels in a million years in so-called carbon cycle. It's a movement of carbon between atmosphere, soil, ocean, living organisms, and fossil fuels. The main mean of transport, so the matter, is the carbon dioxide. Carbon dioxide is a gas naturally present in the atmosphere. However, it is constantly rising. As we can see on the picture in the right, the levels of CO2 differ in history of Earth. And today, we not only have the very high concentration of carbon dioxide, but also the rate of changes is extremely high. So the existing carbon dioxide in the atmosphere interfere with the carbon cycle and disrupts carbon cycle, causing very serious consequences, like global warming, climate change, ocean acidification, sea level rise, and change of ecosystems like coral degradation. And now, the carbon dioxide, which is entering the atmosphere, is not entirely staying in the air. Part of it dissolves in the oceans. So the oceans help slowing down the greenhouse effect on the Earth. When carbon dioxide dissolves in the water, it forms two species. Molecular species, 99% of it, and 1% is reacting with water establishing the weak carbonic acid, which is then dissolving into two dissolved steps, which is described by K1 and K2 dissociation constants, into two ions, bicarbonate ion and carbonate ion, which are then constituting a very, very important buffer, which is stabilizing the pH in water. This reaction we now can see in located in the estuary, and so the estuary is a water body where the river meets the sea. So the fresh water meets the salty water. And in the estuaries, we can observe the horizontal mixing, so the fresh water with the salty water, and vertical mixing, so the atmosphere, oceans, and the sediments. So the three compartments come together: atmosphere, soils, land, and oceans. Because of the a lot of chemical biology and chemical interactions, these areas are very interesting, but also challenging to describe. And this is area of my study. The other motivation for the research was that there is data gathered around the globe about estuaries and in Europe. But look, in the Baltic Sea, where the freshwater discharge is so important for Baltic, there is a lack of information about the estuaries and their effect role on the ecosystems. So the first research spot was I chose the Odra River estuary. Odra River estuary is not only the one of the biggest. Odra is not one of the biggest rivers entering the Baltic Sea, but also very unique. The Odra River waters are flowing into Szczecin Lagoon, which is sort of a buffer between fresh water from Odra and salty water from Baltic Sea. So the fresh water from Odra is not directly going into the mixing with the salty water of Pomeranian Bay. In two cruises, in 2016, in May and November, 4 measurable carbonate system parameters were measured. PCO2, partial pressure of CO2, which is the measure of carbon dioxide content as gas in water, pH as a negative logarithm of activity or concentration of hydrogen ion, total carbon, which is the concentration of all inorganic carbon species, total alkalinity, which is an excess bases over acids, and in parallel, additional parameters were measured, like salinity, temperature, PO2, which is partial pressure of oxygen, nutrition, and particle organic carbon. So, in this picture, we can see the salinity gradients along the Odra River estuary. We got May and November diagram. We can see that they differ, and in these considerations, we use salinity as a tracer of degree of mixing the two water masses, so the salty water and the fresh water from the Odra River. In this picture, we can see the green and the gray curves show the PCO2 levels, which are very high. The PCO2 reached level of 1,000 ppm in water, in river, and in November and in May over 800 ppm. If there was no interactions in the Odra River estuary, it would be around 400 ppm. And then we can observe that PCO2 is significantly dropping down in the Szczecin Lagoon. And the interesting thing is that the PCO2, which is a parameter describing the carbonic system, is, even though the salinity is shifted from May to November, the PCO2 is in relatively the same place. So, 4 measurable parameters are shown here, measured in May and November cruises. They help to describe the carbonate system of Odra estuary, and the bottom two, the pH and PCO2, they are not forming, as you can see, straight lines when comparing to salinity. And but on the other hand, CT and AT, they are forming quite pronounceable straight lines, so they are salinity conservative. So those 4 parameters help us to describe the CO2 system in the Odra estuary, and the CT, so total carbon and total alkalinity, help us for something additional. So we approach to the first separation of biology and chemical influences causing influencing the carbonate system in Odra estuary. The two straight lines you can see here are the total carbon concentration if only mixing would affect carbonate system. They are compared to the values which were measured. As you can see, they differ. And the assumption is that those differences are caused by something else than chemistry. So, the first guess is the biology. And these are two more proofs that the biology is affecting carbonate system in Odra estuary. Same, calculated PCO2 differ from the measured PCO2. And additional, carbon dioxide plotted with oxygen showed the counter-correlation of those two parameters. That means that CO2 is extracted from the water. It's consumed by biology, and in the same time, oxygen is released. So we know a lot about Odra River carbonate system in its estuary, but there are some more questions coming and needs to be answered. Like, is it a single source of CO2 to the atmosphere, the estuary? Is it what role does it play in the overall carbonic cycle of Baltic Sea? Is Szczecin Lagoon a biogeochemical buffer, stopping the organic matter from going straight to the Baltic Sea? And can one separate the chemical, physical, and biological processes influencing the carbonate system? And finally, how does other estuaries look like comparing to the Odra River estuary? So those questions are to be answered hopefully soon. Thank you very much.
Thank you. We have time for 2 questions. So, anybody? No one. So, thank you.
Okay, so now I can invite the next presenter, Michalak, with presentation comparing orientation of geological planes, topological aspect.
Hello everyone, my name is Michalak and I'm a PhD student at the University of Silesia, and my friend Grzegorz is on his 4th year of mathematics at the same university. And our topic relates to 2 branches of science. The first one is structural geology and the second one is topology. Topology is a quite abstract branch of mathematics, but I strongly hope that you will enjoy this presentation anyway. So what are we going to do is that we are searching for a tool that will measure difference in orientation between geological planes. This picture can be treated as a motivation for our research. We can see two kinds of rocks. here we can see a horizontal layer, and below it a fold. And we see that there is an angular unconformity between these two complexes of rocks. And what geologists do, they actually measure the orientation of geological planes. So they are interested in two parameters: the angle of the deep, which is the angle between this line and the horizontal line, and the deep direction, which indicates to which direction a geological plane dips. So, for example, it may dipping to northeast, for example. And geologists can easily measure the angular difference in orientation when we have such situations. So we have the first layer, which is almost horizontal, and the second one is dipping. So it is very easy to assess the difference. But geologists become helpless when it comes to such situation. It's not as easy to assess such unconformity. What is the angle between these planes? So we want to introduce a formal tool for assessing this unconformity. So let's introduce a formal definition of a metric. So I will provide these conditions and then show an example and explain how it works. So we have three conditions. So the first one says that the distance between two objects of a set S is 0 if and only if the objects are the same. The second one can be called symmetry, and it says that the distance between two objects S1 and S2 is equal to the distance between S2 and S1. And the third condition is more complicated, and it says that the sum of such distances is greater or equal than such distance. So let's look at an example. So such function d is called metric if it satisfies all these conditions. So for example, the first condition, we can see that the distance between S1 and S2 is 0. Then the objects are the same. So if we see that the distance between two cities on this map, for example, Gdańsk and Gdańsk, maybe not the right explanation. So if we can see that a distance between two cities is 0, it means that the two cities are the same cities. Okay? But there is opposite implication that says that if the two cities are the same, so the distance is 0. The second one, the second condition says that the distance, for example, between Katowice and Sopot, as I'm repeating, is the same distance as between Sopot and Katowice. So it's the symmetry. And the third condition says that if we insert a city next to them, the Sopot and Katowice, so the distance between Katowice and, for example, Warsaw, plus the distance between Warsaw and Sopot will be always bigger than the distance between Katowice and Sopot. And then we have a similar definition, but you can see that not all the conditions are the same. The first condition is changed. So we can only see that the distance between two objects that are the same is equal 0. So it may happen that we have two different objects and the distance is also 0, which is not easy to imagine. Can you imagine, for example, that two different objects and their distance is 0? It's maybe hard to imagine, but I will provide an example at the end of this presentation. So what we are going to do is we are going to check a hypothesis that we are measuring the angle between two planes, and then we are measuring the sine function of this angle, and we are going to prove that the sine of the angle of the vectors satisfies all conditions for a metric or pseudometric. But why did we choose sine and not cosine? So you can see on this example that we are actually measuring the distance, angular distance between planes, and for planes that have the angle 0, the cosine would be 1. So the value is there was a big distance between the planes, but actually they are parallel. So we can say that their distance should be equal to 0. So we may feel a temptation that we could consider a second function 1 minus cosine, and it's really 0 for parallel planes and 1 for planes that their angle is 90 degrees, but it doesn't satisfy the triangle inequality, because you can open a book or something like that, open a book in a way that the covers form an angle of 90 degrees, and then pick up a sheet of paper and make a bisector. So it divides this angle into two parts, 45 degrees, and you can see that the value here is very small, and the sum of, for example, you may have here 0.2 won't be bigger than 1, which is for 90 degrees. So here we have a graphical explanation what we actually have to prove for the sine, because the first two conditions for a metric are easy to prove, but the third condition, the triangle inequality, is not as easy to prove. Probably you remember, as we were inserting a city, the Warsaw between Katowice and Sopot, and now we are inserting a vector here rather than a city, and we are trying to check that if, for example, we have this vector v and w, and this angle here, and the sine of it will be always lower than the sum of these two sines of angles. So if we prove it, we may use a model and use some application of it. For example, here I'm providing the example that I was talking about. For example, here you have two parallel planes. They are different, but they are parallel. So their distance is 0, although they are not the same plane. So we have two different objects, and their distance is 0. So what other applications may be for this program or project? So I think that the two main applications are that we can find some hydrogeological perturbations. For example, we must take into account that the groundwater table should be orientated very similar to the impermeable layer that is below this groundwater. So if it's not satisfied, it's worth further investigation. It may be also used for detecting erosive events, because subsequent layers are dipping generally in similar direction, but if it is not satisfied, then we may expect that that an erosive event took place. So to sum up, we wanted to find a tool for measuring the angular distance between planes, but not a random tool, but a tool that satisfies all necessary conditions. And our task is to check these conditions. We should also take into account that the sine function is sensitive for small angles. It means that the shape of this function was like that. So it is rising very fast at the beginning, and then it's slowing. So for the planes that are dipping similarly, there will be very changeable results. And for the steeply dipping planes, we would have not such results. And detection of angular unconformities, as I said, between horizon as well as the detecting some erosive events and or hydrogeological perturbation seems to be the main applications. Yes, and the limit of this model is that we still do not know what happens between these horizons. I mean, between these horizons here, we don't know anything. So thank you for your attention.
Hello. Thank you. So we have time for one question. Okay.
Hello. So I have a question. Finally, you are assuming that this is possible, that between two different locations, S1 and S2, is a distance of 0. This is finally possible. Did I got it correctly or not?
It's not possible like in the cities model. Yeah.
Okay.
Because there we consider other formula, but in general, when we construct a formula, that it may happen that distance between two different objects is 0, but we cannot apply it to everyday situations like locations of points in three-dimensional space.
Okay, because on a slide where you have the definitions of pseudometric,
Yeah.
you wrote that it's only possible for two locations, the same locations with the same index of 1. And then you said it's also possible for two different locations. That's why I asked
Yes,
about
it is possible because...
So shouldn't there be a condition in this definition for
No,
S1?
we only say that it is possible. We do not exclude a situation where the distance between two different objects is 0, because the first condition says that the distance...
Okay, so the definition was only for the same locations, so how we can be sure that the location is the same, only when it has the distance of 0? I mean on the definition.
Maybe I do not understand your position right now. So
Because I
yeah.
just wanted to know, first you showed us the definition of pseudometric,
Yeah,
where
yeah.
you wrote that S1 and S1 can have only the distance of 0.
No, it's not. These are not the only. This is not the only situation where the distance between S1, that between distance between two objects is 0. It may it must be that between two objects that are the same, the distance must be equal 0.
Okay, so now I get
But
it.
for
Okay.
for other
So there can
other
be other
objects,
options.
we don't say anything.
Okay, okay, thank you.
Okay, thank you. So next presentation, Mr. Zielinski.
Hello. Hi, my name is Zielinski, and I'm a student at the University of Gdansk. I study geology. I'll be talking about the transport and accumulation of radioactive particles in the Gulf of Gdansk. So, why the Gulf of Gdansk? Why the Baltic Sea in general? The thing about this basin is that it's very unique. We have a gigantic catchment area. It's 4 times as big as the area of the sea itself. It's surrounded by highly industrialized countries, and this means it's a sink for pollutants in general. So here, the picture, beautiful. Radioactive particles. We're gonna focus on cesium here. Cesium is cesium-137 is a very, very interesting particle. It's man-made. It's anthropogenic. It was introduced in the 40s. Well, actually in 1945 during the first atomic test. It's 100% anthropogenic. It's a product of fission of uranium-235. It has a half-life of 30.7 years. Now, is it bad? Yes. Yes, cesium is bad. It's one of the most hazardous substances present in the Baltic Sea. It creates highly soluble salts, which means it can spread through the basin very easily. It's chemically similar to potassium, which means it's easily absorbed by living organisms. And it shows that it biomagnifies through the food chain. This means that, starting from plankton, they absorb cesium, then larger and larger animals eat those smaller ones, and it creates the final product. For example, cod, which we eat, has the highest concentrations of cesium. Cesium has been linked to various diseases ranging from leukemia to benign tumors, birth defects, everything that you can think of which is bad and related to radiation. So, where does it come from? Well, we have 3 main sources of cesium in the Baltic Sea. The smallest is actually nuclear energy. These are point sources. We have nuclear power plants. That's only 4% of the total input into the Baltic Sea. These are nuclear power plants in Sweden and Finland, but also nuclear fuel reprocessing plants. Now, 14% is all the stuff that we produced in the 40s and 50s and 60s during atomic blast atmospheric experiments. That fallout is still depositing directly from the atmosphere into the Baltic Sea. This is 14%, but as you can see, oh, sorry, or not see, 82% of the total cesium contribution into the Baltic Sea is caused by the Chernobyl disaster from 1984. This is a huge, huge percentage. That means that basically nuclear energy and all the things that that activists opposing nuclear energy in Poland are talking about is just ridiculous. So, yes, we have three pathways. We have the point sources, which I just told you about. Those are the plants and reactors. But the two other that we're going to focus on are riverine load and atmospheric deposition. So, how does this affect the total input? How does this work? I mean, what is the pathway? The first one that we're going to talk about is atmospheric deposition. This means that we have noticed a recent change in, well, recent last 100 years or so, in climate changes. Yeah, we've seen an increase in mean temperatures and yearly temperatures. This is also linked to forest fires. Bear with me. I know this doesn't make sense yet, but forest fires produce a lot of smoke, a lot of particles, and they are just generally destructive and dangerous for the environment. They produce aerosols as well as smoke, and these particles, the airborne particles, they contain the radioactive material from the Chernobyl disaster still. How does this happen? The reactor, when it was burning, was producing a lot of smoke. This smoke settled, and it contained, of course, as you can see, radioactive particles, including cesium-137. As I said earlier, cesium has very good bioaccumulative properties. This means that it's absorbed by living organisms easily and stored there. So it lands on the forests, which surround northern Ukraine, Belarus, and the general surrounding area of the reactor. It stayed there. It got accumulated, okay? And then, due to global warming, we see an increase in forest fires. These forest fires they actually re-release the cesium that was deposited in the trees themselves while burning. It releases it and into the atmosphere and causes a direct deposition of cesium and other, well, harmful particles into the environment. Okay, a recent study, actually, 2015, shows actually studied this phenomenon, and these are displayed here. We have the increase forest fire from 2002, 2008, and 2010. We see these are plumes, actually, of radioactive concentrations of cesium. We see this in 2002. This event covered the entire Baltic, well, almost excluding, what is it, the Gulf of Finland? I don't know. Covered almost the entire area of the Baltic. In 2008, it was more local. However, the concentrations were actually quite high. And in 2010, it covered most of Eastern Europe. Now, all of these events are still within the Baltic drainage basin, and this means that this stuff also gets into the Baltic directly, even if it lands on land instead of over the sea. Now, this study didn't include a recent fire from 2015, which was described as the largest forest fire in Ukraine since 1992. And the problem about it was that it burned 30 kilometers away from the reactor. So imagine the concentrations of cesium in the smoke that was being produced from that fire. It must have been gigantic. We're still waiting for data to come in, and we're going to see if there's any evidence of larger concentrations. So the next thing is, due to global warming, as we said before, we have a heightened increase of extreme weather events. Those extreme weather events such as forest fires. And the other one are higher levels of precipitation. This means we get more rain, right? And more rain creates more floods, and gigantic floods flush a lot of material into the sea. Now, as I said before, the Baltic has a very, very large drainage basin. This means a lot of sediment is deposited in it, and if we have more rain, we have more sediment, then this you get the idea of this. This is bad as well. So we have floods. For example, the 2010 flood in Poland, which, if I'm correct, I'm not exactly sure. During floods like these, the Vistula River is able to deposit in per hour. It can deposit the amount of sediment it usually deposits throughout the whole year. There's gigantic quantities of sediment, and this sediment, as I said before, may contain. Just a sec. Oh, here we go. So this is deposited on over land. This the fires, the forest fires, it deposits not only over the Baltic Sea but also on land. So when we get large floods, all of that stuff that was deposited on land and not in the sea, it gets flushed into the river system, into the drainage basin, and it ends up in the Baltic Sea as well. So this is a problem. Here's a diagram of how this works. So this is global warming, riverine load. It's heightened. Everything is yes. The levels are larger now. So the area for research here, which I'm going to do as my undergrad thesis, is I'm going to look for spikes in the concentrations of cesium-137 in sediments from the Gdansk Bay. This means I'm trying to find layers within the sediment that contain larger amounts of cesium. Why? Because we'll be able to, hopefully, correlate these spikes, these heightened concentrations with the extreme weather events. And yes, based on this, we'll probably be able to, or probably, hopefully, we'll be able to predict future trends in cesium concentrations. Now, what we're trying to find here is actually to notice a decrease in total overall cesium-137 concentrations in the sediments. Why? Because of European Union regulations that prevent that lower our pollution emissions, we're probably going to get less cesium in the environment in total. But because of progressing global warming, we're going to get more spikes. These are these heightened levels of cesium, which will be related to the high floods and or forest fires, so the extreme weather events. Yeah, and what I would suggest, this is my personal opinion, what should be further researched if we find the correlation between these events. Okay, but what else we should do? We should measure if there is an environmental impact of these spikes, because due to the overall decrease that we're hoping to find in cesium, we should focus on whether or not there's a significant relation or significant impact related to these spikes of cesium concentrations. Okay, and that's it. Thanks.
Thank you very much. Very interesting presentation. Any questions? Okay, so I have one question. Is there any other radioactive particles in the air than cesium?
Yes, there are many, many different radioactive particles. I'm focusing on cesium mainly because it's researched. And this is only the undergrad thesis, so maybe in my next studies or something, I might focus on a different particle. But cesium is well researched, and it's easy to spot, to measure. So it's just a nice way.
Okay, thank you very much. So the next presenter is Piotr Klejment. Welcome.
Good afternoon, ladies and gentlemen. Let me introduce myself. My name is Piotr Klejment and I am PhD student at Institute of Geophysics, Polish Academy of Sciences. Question where the world is heading is very demanding and the answer is not certain, but because it's very difficult to foresee the future. However, according to me, the future of the science in general lies in the area of supercomputing and the supercomputers. And that is why I decided to present this topic, how supercomputers will give rise to a breakthrough in material science. Let me begin with a short overview, short outline of my presentation. First of all, I would like to talk about the supercomputing arms race, because I suppose we can call this phenomena in this way, because I think that supercomputing power became a new type of strategic resource, as natural resources as oil and gas, and the most developed countries of the world put a lot of money and effort to develop their supercomputers and supercomputers powers. However, there is only one leader currently, it's China, and USA has a big problem to keep up with the China in this global race. Then a few words about Polish supercomputers, because we are very good in this area, and how supercomputers can influence the science in general. And my area of studies is geophysics, how we use supercomputers in geophysics and how it provide new approach to our science. And finally, some conclusions and summary where the world is heading. So the supercomputing arms race. As we can see on this figure, from the 1993, every year there is a presented list of top 5 supercomputers, the best supercomputers of the world. Here we can see this is a unit of how supercomputer is fast. This unit is a flop per second. It means how many calculations supercomputer can do in 1 second. As we can see, there is a significant increase in this increase is also a constant during every year. And here is a table with countries, worldwide number of computers by country, and as we can see, there are 2 global leaders, it's China and United States. But as I have heard, because this survey is from November 2016, currently China has got more supercomputers than United States. What is a great achievement, because 15 years ago China has got no supercomputer. And we can be proud of place of Poland on this list, because Poland holds 7th position in global list of supercomputers, because we has got 7 supercomputers. Most of them has been launched in previous several years. As I can see, the champion is only one. This is China. In previous year, they launched a new supercomputer. As you can see here, this supercomputer replaced other leader, also from China. What is interesting, and I'd like to draw your attention to the fact that this supercomputer was made only from components made only in China, because previous supercomputer was include also components prepared by USA Intel. And as we can see, there is a huge gap between USA, the fastest supercomputer, which has 17 teraflops, and is the fastest supercomputer from China, which has 93 teraflops. And now several words about Polish supercomputers. We have got 7 supercomputers. There are BEM, Zeus, Prometheus, Iglo, Triton, a computer in National Center for Nuclear Research in Świerk, and also Okeanos in Warsaw. This supercomputer is the newest one. It started its activity in previous year, and I am the most familiar with this supercomputer because we performed our simulations on Okeanos supercomputer. However, the fastest one is Prometheus in Kraków. So we have got a lot of these supercomputers. However, how can they influence our science? I can say that almost every of you can use supercomputer to your simulations, because supercomputers are used in wide variety of areas, from business. Business is especially interested in big data analysis, to, for instance, cosmology, to check what are the universe origins and so on. Maybe countries are so interested in investing in supercomputers, especially for this military science, because this is especially important in military technology. However, there are a lot of options where we can use supercomputers and how they can influence on science, how they can improve our results, and how they can give new approaches to our technologies. I am especially interested in the area of geophysics. However, in geophysics we also have a lot of unsolved problems, like, for instance, earthquake prediction. Currently, state of art is that we are completely not able to predict earthquakes, and despite the years of efforts. And we trust that if we combine possibilities of theoretical physics, mechanics, informatics, and supercomputing, it can give a new approach to our area of science. It means to geophysics. So let's take a closer look at our geophysics problems. As we know, or we don't know, however, a super earthquake looks like as is shown on this figure. But the biggest problem with earthquakes is that we do not understand what exactly is happening in the earthquake source. That is why we are interested also in material sciences, because inside there, deep down in the earth, there are rock masses which are under huge external forces. There are pressure or so on. And due to movement of rock masses, earthquakes occur. However, as I said, these processes in earthquake sources are not well known. So that is why we suppose that numerical simulations can provide a new approach to this problem. We decided to use discrete element method, which allows to study time evolution of system, and that is why we, for instance, we don't use finite element method. So let's take a closer look at the more technical details of our simulations. We use open source software called SysParticle. This software is very comfortable and very convenient for us because it has implemented message passing interface, which is very important because it allows to run our simulation on multi-core stationary computers and to use all cores of these computers, and also it can be used on the supercomputers. This is a big advantage of this software. The engine of the SysParticle is written in C++, however, and there is also included very comfortable Python wrapper. As we can see, here is an example of code in SysParticle, and with this code we can obtain simulations like we can see here, because everything consists of particles, we can simulate nearly everything with our simulations. Here are a set of equations. Basic idea is that we use Newton equation for linear movement, Euler's equations for rotational movement of particles, and here is the algorithm for the computer, how to calculate forces, velocities, and so on particles in every time step. We tried, this is a practical example of our simulations, we analyze a Brazilian test. In fact, this is not very connected with Brazil, but the inventor was from Brazil. This test is very important for testing rock masses, brittle materials in general. That is why we are interested in this area. Here are some our results. This is a laboratory experiment, and we are very satisfied with our achievements because this is our simulation on a supercomputer. And as you can see on this two-dimensional picture, we can see that we have the same fracture propagation as in the experiment. And some results. We carried out a lot of experiments. For instance, we tried to analyze how fast fracture propagation in our simulation is, and we checked what is the influence of, for instance, grain sizes. What is the ratio between grain sizes in the sample to obtain brittle material, and how this fracture process goes on in materials in which we are interested in. And finally, so where the world is heading. As I said, we trust that supercomputers are our future and future of the science. It allows to, especially in the area of materials science, because it allows to create new materials, design new materials, or what is important for me, to have a deeper insight into processes in materials like in rock masses, what is extremely important in case of earthquakes and in general in geophysics. And to answer the question where the world is heading, so I suppose that we are entering the golden age of material design, because our supercomputers are faster and faster. We can simulate more and more with this massive, huge computational power. So thank you very much for your kind attention.
Thank you. We have time for questions. No questions. So thank you. And the last one, Mr. Grabowski.
Okay, so welcome again. My name is Miłosz Grabowski. I'm a PhD student here in Institute of Oceanology, Polish Academy of Science. Also, I'm a member of Sopot Scientific Association. My field of work is focusing around non-invasive methods of seabed examination. And basically today I would like to show you what we can find on the bottom of the Baltic Sea. And by the end of my presentation I will try to answer the question where the world is heading. So, topic of my presentation is impact of anthropogenic pressure on the southern Baltic Sea bottom. But actually, what is this anthropogenic impact? Well, in my opinion, it is all actions which humans are taking on the sea, and of course those activities left some marks. So I classified this anthropogenic impact into four main classes. So the first one is trow marks. Trow marks are roasts left by the fishermen on the sea bottom, and we can distinguish fresh browsts and old browsts. and I will show it to you later. Then we have some garbages or garbage. Of course, we can find garbage everywhere, even on the bottom of the sea. So I will try to show you some examples of it. Then we have shipwrecks. Of course, ship are always occurs on the Baltic Sea and on the other seas and oceans. So from time to time it happened that some ship is sinking. Then we have shipwrecks. And last but not least, dumped weapon. So I don't know if you are familiar with that, but after Second World War, really tons of ammunition, both chemical and conventional, were dumped on the deepest part of Baltic Sea. And well, it's my job to find it and to identify it. So we have also conventional ammunition and chemical ammunition. Oh, and in terms of garbages, we have different types of wastes. I mean, big wastes, and of course we have some ghost nets. Area of data collection. I've decided to distinguish 3 areas where we conduct our survey. First one is Gdansk Deep, another one is Bornholm Basin, and the last one is area near German coastline. This area is called Kolberger Heide. Of course, in those areas we have different types of sediments which are building the seabed. In Gdańsk Deep we have rather hard sediments from sand to fine mud. Average deep there is 90 to 110 meters. Different situation is in Bornholm Basin. There we have some soft sediments like fine mud and clay and so on. Average deep there is similar to the Gdańsk Deep. Also we have a very strong current there, and the visibility there is very poor, but you will see it later. And then we have really rather shallow place, which is Kolberger Heide. Depths there are from 5 meters to 30 meters. We have high biodiversity there and rather hard sediments. Of course, as I mentioned on the very beginning of my presentation, I'm using non-invasive methods to investigate the bottom. So a good example of this method is a hydroacoustic survey. So I'm using acoustic impulses to generate image of the bottom. So we have some pretty fancy device which are generating sound. The sound is scattering on the surface or even on the sediments. Then I obtain just a picture. Actually, it's just a picture composed from with pixels. Those pixels has its value. It's quite similar to the traditional cameras, but it uses sound to generate those pictures. This device is called side-scan sonar, by the way. Side-scan sonar is usually towed behind the research vessel, and then we are collecting data. Of course, we obtain two-dimensional data, so we can only look for our bottom like from up, from the surface above the bottom. So we can distinguish some structures on the bottom, like boulders, gravels, and so on and so on. Here you can see some examples of different types of bottom on the collected with the side-scan sonar. So, as I mentioned before, here is our first toy, actually. It is towed side-scan sonar. We are using it mainly to obtain pictures from big areas, but the resolution isn't very good due to frequency, which is 100 kilohertz. The principle is that if the frequency is growing, then we have better resolution, but the range of the image is lower. Well, it is really good piece of device. We are using it mainly to perform preliminary survey to detect some big obstacles for another device, which is autonomous underwater vehicle. Actually, it is a robot, like drone, underwater drone. My job is to plan a mission for it and to run it, launch it, and recover it. It is equipped also with side-scan sonar and with the magnetometer. The side-scan sonar is working with higher frequencies, as you can see. So, as I mentioned, we can obtain bottom images in really good resolution. Let's go further. When we conduct our survey, our acoustic survey, we need to examine what we are found. So to do it, we need to use a remotely operated vehicle, because we are operating in the areas where depth is so great that divers can't work there. So that's why we are using our remotely operated vehicle. It is equipped with some traditional cameras, some LED lights, and some other acoustic device to local, maybe not to local, but to find those objects which were selected based on our acoustic images, and then it is possible to locate them. So, of course, when I'm collecting my data, it needs to be processed first. So first thing is to proper track the data. Other thing is to perform normalization of data to obtain proper gains. And third thing is to perform semi-automatic bottom classification. It is based by algorithm which I create in MATLAB software, and also with the software which is available commercially. So based on this algorithm, I can distinguish different types of sediments and objects which are laying on the bottom. So here, as you can see, those white objects are just the targets which we are looking for. And then I can perform my targeting. So as you can see here, there is a piece of sea bottom and something is laying here. Ready results looks like this. So I have a map of area which was surveyed, and I've got some targets marked here. Of course, here's the result of classification. So it helps me sometimes, but usually I'm using this targeting procedure. Okay, so in terms of this anthropogenic impact, as I mentioned before, we have some trawl marks. They are everywhere. So if you look on our sea bottom on Baltic Sea, every single square meter of bottom is marked with those trawl marks. They are literally everywhere. We have some garbages. Of course, these are data from Gdańsk Deep. Here we can see some old tire or old iron container for some gas. Sometimes it's pretty tricky to establish origin of those targets, but as you can see, it can create a good habitat for those two little cots and for other biota. Here we can see some big objects, like, I don't know, it's kind of iron cabot from the ship, placed on the sea bottom. Here you can see a shipwreck. Ghost nets. Ghost nets can be really treat for the divers, for our equipment. It usually occurs in the area of shipwrecks, but actually we can find it everywhere. So here's the good example of ghost net tangled in the propeller of our ship, which is Oceania. Of course, it generates problems. We need to clean up those propellers and so on and so on. We have some shipwrecks. An example from Bornholm Deep and from Gdańsk Deep. And then we have also those very important chemical warfare agents dumped in the Baltic Sea, which can be really, really bad thing. Here you can see a pile of mine and a picture from the ROV where it occurs. Those pictures are from Kolberger Heide, and here you have some picture of some conventional munition. Of course, it occurs also in Gdańsk Deep. So, yeah, it can be really danger for us, for everyone. To conclude, acoustic methods conducted with visual inspection techniques are relatively fast, accurate, and cost-efficient way of sea bottom examination. Of course, in my opinion, it is the fastest way to conduct this type of survey. Strong anthropogenic pressure can be observed in all regions of Southern Baltic Sea. In areas where anthropogenic impact can be treated for marine activities, weapon dump site, the monitoring should be established. Well, it is established right now. Marks of human activity on the sea bottom, such as trawl marks and objects placed on the sea bottom, are creating new habitats for the biota, as you see, for example, those coats and so on. Human activity on the Baltic Sea is still increasing, hence different regions of the all Baltic should be investigated. And to finish my presentation, I would like to answer the question where the world is heading. So, in my opinion, world is heading to be a better place, to be a better place for our children, and to obtain that point, we need to know the world very well. And Baltic Sea and other seas and oceans aren't very well known, so in the future we need to more stress this need of knowledge. So that's all. Thank you very much.
Thank you very much for your presentation. We have time for one or two short questions. Do you have some information about the Northern Baltic? There is some garbage also.
Yes. Well, I select those areas like Gdańsk Deep, Bornholm Deep, and Kolberger Heide because, in my opinion, those data were the most interesting. But of course, oh yeah, here it is. For example, very similar investigation was conducted here in Gotland Deep and in northern part of Baltic Sea. So yeah, we have this type of data, but I select only this one for today's presentation.
Thank you very much, and now
Thank
we
you.
have time for coffee break, so invite you for 15 minutes break.